Saving energy in the building sector and automotive industry is a major global socio-economic target in energy efficiency as well as environmental point of view. Hello, good evening all. This is Safna from Material Science Laboratory of Eester2020 College, Kerala, here to present a poster on tailoring of optical bandgap and microstructure profiling of vanadium-based complex compound systems. Vanadium pentoxide have recently been acquired a great deal of attention in diverse device applications due to its outstanding properties. The non-stoichiometry associated with V2O5 can be used to modify its properties, and suitable ions may be incorporated in the crystal matrix without affecting the crystal structure drastically. Here we synthesize of VBIO and VMNO complex compounds by solid-state reaction technique in the temperature range 540 degrees Celsius to 640 degrees Celsius and carried out different characterizations such as XRD, UV visible, photoluminescence spectra. And this is the X-ray diffractogram of the as-prepared samples. This is for bismuth and this is for manganese. And XRD shows peaks analogous to pure V2O5 along in different planes. It shows a dominant peak at 2 theta equal to 20.54 degree along 001 direction. And all patterns are high in intensity and sharp, which has improved the crystalline quality of the samples. And all samples show same phase and structure as that of pure V2O5, which can be indexed with orthorhombic structure in PMMN space group. And obtained data shows insignificant variations in lattice parameters, suggesting successful insertion of manganese and bismuth ions in V2O5 matrix lattice. And this is the diffuse reflectance spectra of the prepared samples. It shows a sharp absorption edge from 500 nanometer to 650 nanometer, and there is a slight variation in reflectance edge. This is maybe due to the bandgap restructuring, which alters the conducting behavior of the samples. And this is the estimated bandgap energy using Kubelka-Monk function, and with increasing the mole fraction, the bandgap energy of VBIO system increases, which can be explained using Morse-Bernstein effect. While in the MNO system, as S increases, the bandgap energy decreases, since as free carrier concentration increases, the bandgap widening is counteracted by a narrowing caused by the correlated motion of charge carriers and by their scattering against ionized impurities. And this represents the PS spectra of the prepared samples at room temperature. This is for bismuth and this is for manganese. Major emissions were observed around 370 nanometer, 390 nanometer, 400 nanometer, 460 nanometer, and 535 nanometer. The emissions have been mostly attributed to the radiation transition between electron-hole recombination. The emission at 370 nanometer is due to valence uncertainties of vanadium, and at 400 nanometer indicates excess presence of V4 plus ions along with V5 plus ions in crystal. And 460 nanometer emission has an energy higher than bandgap energy and might be due to recombination of electrons from high levels of valence band and conduction band. And the low intensity indicates oxygen deficiency related defects in the crystal. All these emissions are relatively strong and broad, and this is an extremely desirable feature required for different sensor applications. So here we synthesized of VBIO and VMNO complex compound. All samples have orthorhombic structure with prominent orientation along 001 direction and matches with pure V2O5. Bandgap energy calculated matches well with reported bandgap of metal oxide substituted V2O5, and the photoluminescence spectra optical bandgap is found to be restructured due to the presence of bismuth and manganese ions. Thank you.